Right, so I'm going through a paper 2 today on request, so I have to make this video really fast because I don't have a lot of time to do it. But yeah, anyways, I'm gonna go through the whole paper 2, but instead of actually going through all the questions and solving them, I'm just gonna like explain how to do them, and then we'll check with the mark scheme to see if it makes sense. Right, so the first question is a titration question, which is basically just some calculations involving moles. So you can pause and read through the instructions if you want to. It's basically just explaining a thiosulfate titration and like how it was done and the data they got. The first question is calculate the volume of thiosulfate required to react with iodine to reach the endpoint. So it's basically just reading off the data, but something to notice is that the first titer is just a rough titer to like approximate how much you need to titrate for the second and third. So it's common practice to use the first titer as a rough titer, so just don't involve or don't include the data for the first titer for the average volume used. So to calculate the volume used, you just take the difference between these two values, add it to the difference between these two values, and then take the average, which is dividing by 2 in this case. And we can confirm this by looking at the mark scheme. Yeah, they just take the difference, add them together, and then multiply by 1/2, which is the same as dividing by 2, and then you get the answer. Right, for the next one, calculate the amount in moles of thiosulfate. So we can use the formula, which is just N equals CV, and we have the volume from this question, and the concentration is 0.1. So just remember to convert the milliliters into liters by dividing by 1000, and then just multiply with the concentration. And yeah, that's what they've done. This is the volume in milliliters divided by 1000 to get to cubic decimeters, and then multiplying by concentration, and then you should get this value. Okay, next, calculate the concentration. Calculate the concentration in moles per cubic decimeter or moles per liter of hypochlorite ions in the diluted bleach solution. So it's basically the same. We know how many moles of thiosulfate we have, and if you look here, we see that they react 1 to 1. Oh, hypochlorite. Well, let's see here. Hypochlorite reacts to produce 1 mole of iodine, and 1 actually reacts with 2, so I was wrong. It reacts 1 to 2. So for every mole of hypochlorite, we have to use 2 moles of thiosulfate. So we have half the moles of hypochlorite as we have thiosulfate. So we take the moles we got here, and then we divide by 2, and then we to get the moles. So the formula for concentration is C equals N over V, and this N is the same as this, but divided by 2, and then you divide by the total volume, which in this case is 25 milliliters, which you also have to convert into decimeter cubed. So let's see if that's correct. Is this one right? So we multiply by 1/2 and use the moles here, and then we divide by the volume, which in this case we flip the fraction, so we get 1000 on top. So yeah, then we get this as the answer. Okay, calculate the concentration of the undiluted bleach solution. So the first step of this procedure was diluting the solution from 25 milliliters to 250 milliliters, which is diluting it 10 times. So if you want to go back, you have to multiply the concentration by 10. Or you could use the CV V1 or C1 V1 and C2 V2. Then we have these two values, and we know the initial volume, and then you solve for C1, and it should be 10 times as much. So the mark scheme yeah, they just straight up multiply by 10. So you just get 10 times the concentration. Okay, next question. Some of the group 17 elements, blah blah. Okay, deduced oxidation states of chlorine and iodine in the following species. Okay, so we know that because oxygen is very electronegative, it's usually always -2 in oxidation state, except for some circumstances where it's not. For example, if it's bonded to fluorine. Alright, but sodium is also usually +1 because it's very electron positive, or it's very not electronegative, which means that chlorine is most likely -1, no +1, because +1 + 1 has to equals, or +1 + 1 -2 has to equal 0 because it's uncharged. So it's probably +1, or it is +1. And for iodine, it's 0 because it's not charged. So if you wanted to have two charges plus together which are equal and they add up to 0, it has to be 0. So it's +1 and 0. Which, yes, +1 and 0. Great. Deduced with a recent oxidizing agent in the reaction of hypochlorite ions with iodide ions. So the oxidizing agent is something that reduces itself to oxidize something else. So if you go to see what has been reduced, well, this has -1 and this one has 0, so the iodine has been oxidized, while chloride goes from +1 here to -1 here, so this one has been has indeed been reduced. So the hypochlorite is the reducing agent. No, the oxidizing agent, I mean, because it was reduced itself. So, yeah. Hypochlorite is the oxidizing agent, I think. Yeah. Okay, next question. From a health and safety perspective, suggests why it's not a good idea to use hydrochloric acid when acidifying the bleach. Okay, so right, if we in this case use chlorine instead of iodine, we will actually produce chlorine gas. Let's see if I can write the equation. So it should be Cl minus plus HCl goes to chlorine gas, and what else? Let's see, water, I guess. And this should then be balanceable somehow. And then I also think I like this. Something like this, you have to write out the half fractions if you want to make sure. But the point is that it produces a chlorine gas, which is stated in here, produces chlorine gas, which is toxic. Right? Oh, it should have been this question, not this question. Next question, which is, well, question events. Anyways, the thiosulfate ion, blah blah, has an interesting example of oxidation states. The sulfur can be considered to have an oxidation state of +6 on one atom and -2 on the other atom. Discuss this statement in terms of your understanding. Well, I think the point of this question is just to explain how oxidation states are really just something we attribute to molecules, and that it's not like I guess intrinsic to the molecule. So it's just a way we understand how electrons are distributed within the molecule. So I really have to look. We can look at the arguments they state. Well, oxidation states are not real, just used for electron bookkeeping purposes. Average oxidation states bonded differently. Well, yeah, a bit of a weird question. Next one. With reference to the combustion reaction of methane explore two different definitions of oxidation, choosing one which is valid and one which may be considered not valid. Okay, so the valid one is at least that if you have a transfer of electrons, it's a oxidation state, or if there's a change in oxidation states, I mean, it's a redox reaction. The not valid one is really weird. I looked at the mark scheme, and it just says loss of electrons might suggest formation of ionic product, but not valid since CO2 is covalent. Or loss of electrons might suggest formation of ionic products, but not valid since reaction only involves neutral molecules. I think it's a very weird reaction that weird question that you're required to come up with something which is wrong, but anyways, that's what the question asked. Okay, next one. State a condensed electron configuration of sulfur. Sulfur is number 16 in periodic table, so 16 electrons. And then you should remember how to write like the orbitals. But it also asks for a condensed electron configuration, so we have to know the noble gas before it, which I think is neon. I don't know if I have a data booklet up. But anyways, I think it's neon, so let's just write neon. Let me check actually. Yeah, neon. Which is 10, so we need 6 more. Let's just write the whole thing. So 1s2, 1s2, 2s2, 2p6. So this is the neon. 3s2, 3p, 3 to get 3p4 to get 16 electrons. So neon and then 3s2, 3p4, which I think should be great. Yeah, great. Next one, deduce the orbital diagram of sulfur showing all orbitals present. Well, it's basically just the same. We have the 1s, all orbitals. Well, I don't know if I have space to do that, but you have the 1s, 2s, then 2p. Well, it's just 3s, 3p. And then you just fill the orbitals with electrons. So this would be the neon core. And then you distribute electrons in the p like this. So that's the orbital diagram of sulfur. Okay, finally done with first question. Second question. One of the main constituents of acid deposition is sulfuric acid, as it is formed from the sulfur pollutant SO2. Then some radical reaction. State what the symbol dot represents in the species. Well, it represents a radical which is a unpaired electron. So yeah, pretty simple. Consider the following equilibrium between the two oxides of sulfur. Predict within a reasonable direction the position of equilibrium will shift for each of the 3 changes listed below. Alright, so it's a equilibrium question. First statement, increase in temperature. Well, it's a exothermic reaction, so this way increases the temperature and this way decreases the temperature. If we want to increase the temperature, or if we increase the temperature, it wants to go the other way by to decrease the temperature by the whatever law. I don't even remember the name. I don't remember the name, but it says something like that the reaction will oppose whatever change you do to the reaction. I don't really remember the statement. Anyways, it shifts to the left. To decrease the temperature is the reason. So increasing pressure, the same kind of logic. Here we have 3 molecules of gas, here we have 2. So if you increase the pressure, it wants to decrease the pressure. And this is done by going to the right because it has 2 molecules while it has 3 here. So right. And addition of catalyst, no change. the catalyst never changes equilibrium in any kind of way, because it changes the path equally in the forwards and the backwards direction. So like overall it doesn't change the equilibrium in any way. Okay, next question. Sketch the energy profile of the forwards reaction to show the effect of the catalyst on activation energy. Well, just notice that it's exothermic, so it goes something like this. And if you want to show the catalyzed reaction, you just draw the same one but with a lower activation energy. And then you have to label this ECAT or something. Oops. Yeah. And then just write uncatalyzed for this one. Okay, the other compounds present in the acid rain are formed from nitrogen dioxide. Formulate an equation for the reaction of nitrogen dioxide with water. So it's just nitrogen dioxide plus water, actually 2, because they react to form nitric acid and this compound. So let's check if it's balanced. We have 2 hydrogen here, 2 hydrogens, 2 nitrogens, 2 nitrogens, and then 5 oxygen and 5 oxygen. It's just an equation to remember, really. Okay, with reference to section 9 of the data booklet, explain the difference between the atomic radius and the ionic radius of nitrogen. So section 9 just shows the values of the ionic and the atomic radii. So the difference is because the ionic radius, which I guess would be 2 minus for nitrogen, it has a larger radius because there's more electron repulsion if you fill the outer shell. Okay, question 3. 0.212 moles of sodium methanoate solution dissociates completely into its ions. Formulate the equation including state symbols for the equilibrium reaction of the hydrolysis of methanoate anion. So what I think the methanoate is basically just this, I guess. No, not even that. Just a hydrogen here. So it's technically just methanoic acid but an ion. Well, let me check that. Yeah, we did all of these ones. And this one. Yep. It's the methanoic acid anion. So HCOO minus plus OH minus, because it reacts, no, hydrolysis of course, so it's not like that. Oh, oops, wrong again. COO plus H2O, and this should react to form, it's a acid base, or the water reacts as a acid. So it remakes, it's equilibrium of course, regenerates the acid, and then you get the hydroxide. Okay, calculate the Ka of the dissociation constant for an aqueous solution. Okay, it says you need section 21, and section 21 gives the pK. I don't complete. Let's see what the pK is here. Well, I don't know if it maybe each probably gives you the pK because it says that you're supposed to find a K. And the way you find K from pK is you take the negative log of 10 to the minus pK. Is how you find the K. Yep. So just use the value you find in the data booklet. Next one, calculate the KB. So use this relation and then rearrange for KB equals KV over Ka, where Kv is 10 to the minus 14. And Ka you find here, so then you get Kb. And that's how they also do it. So yeah, quite simple. Next one, 3-mark question. Determine the concentration of hydroxide ion. And mention one assumption. So we have the reaction, which is HCO minus plus H2O, and then equilibrium to the acid and the hydroxide. So use the equilibrium law, where you have initial change and equilibrium. Initial concentration of this is 0.12, and these two are 0, and then this changes by x, and these two increase by x, so you get 0.12. Whoops. 0.12 minus x, and then xx. And you ignore water because the Ka, like the expression here, is products over reactants for the equilibrium, but Ka equals the K times the water. So the water is just moved to the other side, so you just ignore the concentration of water. And now you just set up the equilibrium expression, where you have x squared, and then 0.12 minus x. And the assumption now is that from the pK or the K we found, it's quite small, so we can just assume that the x is a lot smaller than 0.12, so then we just ignore the x, and we get x squared over 0.12, and then just equals Ka, of course, and then you just solve for x squared to get the concentration of hydrogen, or what is it called again? Hydroxide, of course. Ions. Yep. So that's also what they do here. And then you get this answer. Next question, calculate the pH. Okay, so we found the concentration of hydroxide here. So you just take the minus log of hydroxide to get POH, and then use the 14 equals POH plus pH, rearrange for pH, and then you should get the answer for POH. No, pH, because you have a POH from this. So the answer turns out to be 8.41. Question 4. 1-iodoethane reacts with sodium hydroxide. Explain the mechanism, using curly arrows to represent the movement of electron pairs and showing any stereochemical features. Okay, so it's a 4-mark question. Let's zoom it so it's easier to draw. Okay, so 1-iodoethane. I usually draw condensed formulas because I'm a bit lazy. Oh, also show stereochemical details. So let's just draw it like this then, for the time being. It's probably not the most convenient way of drawing it. Let's instead draw it like this. Yep. And then we have the hydroxide approaching from here. And also remember to draw the arrow from the nucleophile, which in this case is the hydroxide. And then with attack here, which will kick out the leaving group. But we also need to draw the transition state to get full marks. So it would be something like this, or you don't actually do that, you draw the dotted lines like this for the transition state. And then the two hydrogens with a negative charge, and then you mark it with the double dagger for transition state. And then this goes to it's an ascent to reaction, so it changes the stereochemistry. So I didn't draw this one too well, but it at least should push the OH in front, and then the other hydrogen in the back. So it changes the stereochemistry from this to this. And I think that should... Oh, you don't have a negative charge here, do you? No, you don't, because the iodine leaves with it. Okay. I think it's better visualized here, because it's supposed to attack from the back, which my drawing doesn't demonstrate too well. But anyways, you have the hydroxide attacking here, kicking out the Levy group with this type of transition state. Then the stereochemistry reverses. And that's all you need for 4 marks. Oh wait, it actually does say 180 degrees. Partial bonds 180, so yeah, my drawing is kind of trash. So you should kind of draw the hydroxide attacking from here, which does make more sense from my drawing. It's just that I drew it really bad. So yeah, just make sure to know how to draw these kinds of things, I guess. Okay. Next question. State the rate expression for the reaction and identify the molecularity of the rate determining step. Okay, so it's SN2, which means that it depends on the concentration of both reactants. So rate equals K, the concentration of OH minus, times concentration of CH3 CH2I. Yeah, and then molecularity is bimolecular. Yep. Next question. Suggest why polar aprotic solvents are more suitable for SN2 reactions, whereas polar protic solvents favor SN1. Okay, so for SN2 you need a nucleophile, and the nucleophiles are stabilized by hydrogen bonding, for example, in polar, or like just polar stabilization or hydrogen bonding stabilizes the nucleophile, which makes it a worse nucleophile, which decreases the rate of reaction for SN2, which means that you would rather use aprotic solvents. Oh wait, are polar aprotic solvents. Okay, so aprotic solvent is able to form hydrogen bonds. So you want it aprotic to not form hydrogen bonds to stabilize the nucleophile. But it's the opposite for SN1, because for SN1 you would end up with a carbon cation, which you want to stabilize. And it may be stabilized by hydrogen bonding, for example. Yeah, decrease nucleophility due to hydrogen bonding. And stabilize, okay, solvate the intermediate carbon cation. Okay, so next one, deduced with the reason if water or DMF is a better solvent. So a DMF is aprotic and diethyl formamide. And water is protic. Oh, it also gives you the structure, which is something like this. I think for DMF. It's supposed to be aprotic at least, while water is protic at least. Yeah, this is of course aprotic, has no N2H or O2H, while water has a 2O to H bonds. So this is a SN2, which means that you want aprotic, which means that DMF would be a better solvent. Yeah. Okay, describe what you understand by the term frequency or pre-exponential factor A. So this is referring to the pre-exponential factor in the Arrhenius equation, which I think is K equals A to the E to the power of minus activation energy, I believe, and RT. So the pre-exponential factor here is a frequency. It accounts for the frequency of collisions and the probability of the collisions being in the right geometry. Yeah, frequency of collisions and proper orientations. Right. And then you get a question on Arrhenius equation. You get the activation energy, and you get the pre-exponential factor, and then you're supposed to calculate K. at temperature 25 Celsius. So the only thing here to remember is to convert this into Kelvin. And then you just put it in, and then you get the answer. Oh. And use the correct units. And you find the units by rearranging the units for this equation. So the rate is in concentration per second, while these two are both in concentration, so concentration squared. So the units units for K turns into 1 over second and the concentration. So it's concentration is in moles per decimeter. So if you divide by that, you get decimeter per mole, and then per second from dividing by time. This should be T, of course, not S. The unit is S. So oops, that's how you get the correct unit there. Okay, next question. Yeah, here. Many automobile manufacturers are developing vehicles that use hydrogen as a fuel. Suggest why such fuels are considered to cause less harm to the environment than those with internal combustion engines. You just explained that the product of hydrogen as a fuel is water, which is considered a less harmful greenhouse gas than carbon dioxide, for example. I'm not sure what they explain. Yeah, okay, only water produced non-polluting. Yeah. Hydrogen can react with ethane to form ethane. Using average bond enthalpies, calculates change in enthalpy. So just look at the data booklet, says section 11, and use the equation, which is bonds broken minus the bonds formed. And you should get the correct answer. Let's see here. Yeah, just breaking and formation. And then make sure to have the right amount of bonds. For example, H2,4 would be like this. And then you have to count the correct bonds. So you have 4 C2H and 1 C double bond C. Okay, ozone, dinitrogen, blah blah blah. All examples of greenhouse gases. Draw one valid Lewis structure for each molecule of the greenhouse gases listed. So you should know by now that ozone looks like this. And it's technically a conjugated structure, or a what is it called? Anyways, yeah, it's like half bonds. So yeah, but this is how you would draw the Lewis structure. Oh, resonance structure, of course. It has a resonance structure. And for sulfur hexafluoride, hexa means 6, so I have a whoa, very ugly. Let's see, this would be better. 6 fluoride atoms around the sulfur. Yeah. Well, if you want to draw the Lewis structures, you would really count up the valence electrons first, and then make sure that they all obey the octet rule. And if there's anyone left, you just put it in the central atom. But I don't think there's anyone left in this case. So yeah, that's how they look. Okay, deduce the name of the electron domain geometry, and molecular geometry. So for ozone, all the oxygens are trigonal planar, or trigonal planar. This one is as well, because if you draw the resonance structure, double bond could also be here, which makes this. No, I mean this one, of course. If you put a double bond here, this one, which is which is right now. Oh, shit, I forgot. Should be like this. Right now it's tetrahedral, but if you draw the double bond here, it also turns trigonal planar. So that's the answer for this one. Molecular geometry is bent or V-shaped. For this one, electron domain geometry, hexa or hexagonal, because it has 6, and it's the same for the molecular geometry. or octahedral, of course. Just stupid, I guess. Yeah, it's octahedral, because that's what the shape is called. You have like a plane here, and then one on top and one on the bottom. And then if you connect all the lines, you get 4 planes on the top and 4 on the bottom, which is why it's called the octahedral. Yeah. Bond angles, I guess this question does not ask for bond angles. Oh, it does here. Identify which molecules given in part A1 has an extended octet of electrons. So it's pretty simple to see that this one has more than just 8, because it has 6 arms, which makes it 12 electrons. So the sulfur hexafluoride. Yeah. Bond angles. So ozone has a bond angle 115 to 120 as accepted answer. So just answer something in between there to be safe. While hexafluoride has angles 90 and 180, depending on which of the angles you look at, because you do have like the one between the sulfur and the fluoride here, this is 90, but the one between here and here is 180. So we have 2 different angles. Next one, draw all the resonance structures. So one is like this, and the other one is the same but the double bond here instead. And then lone pairs, 2 here to make it 8, 2 here, and then 3 here, and same here. Yep. And you can also draw some like arrow like this to show conjugation or resonance structures. Next one, nitrous oxide can be represented by different Lewis electron dot structures. Deduce the formal charge. Okay. So formal charge equals valence electrons minus non-bonding minus bonding electrons divided by 2. So formal charge on oxygen on left hand side. Oxygen has 6 valence electrons, and then you take away 4 minus 2, so 6 minus 6 equals 0. Formal charge on nitrogen. Nitrogen usually has 5, and then you take away 4, so it has 1. This one also usually has 5. You take away 4 here and take away 2 extra, so you take away 6. 5 minus 6 is minus 1. And same business here. You have 6, take away 6, take away 1, minus 1. You have 5, take away 4, so 1. 5, take away 2, take away 3, 0. Here, 6, I mean, take away 2, take away 3, so plus 1. 5 minus 4, 1. And 5 minus 6 minus 1, so minus 7, minus 2. So that should be the formal charges. 1 minus 1, minus 1, 1, 0. 1, 1, 2, yeah. Great. Formal charge can be useful in electron bookkeeping. Electron negative values are ignored when FCs are assigned, which is expected to be the preferred structure. So firstly you want to minimize the formal charge, and then you want the formal charge to add up to the charge of the molecule, and you want the most electronegative atom to have the negative charge, which in this case is the B structure, because oxygen carries the negative charge, and we have minimized the charges. So probably B. Smallest difference for A and B, so either is preferred actually. Oh, but B is preferred as oxygen is more electronegative. Yeah, so you have to use both arguments to get the 2 marks. Okay. Next one, ozone in the atmosphere can be formed from the combustion of methane. State the equation for this combustion reaction. So methane is CH4, and then you combust it. Then you get methane plus water plus CO2. And then you have to balance this, and there's actually quite a lot of way to balance it because you have isolated oxygens on both. But I'm pretty sure the way the books or the answer mark scheme wants it is like this. So now we have 4 hydrogens, and then 6, 7, 8, so we multiply this by 4. Oh, 5. Did I count wrong? Oh, yeah, of course, here as well. So 10 actually. So 5. Yeah, so that's the reaction they want. Calculate the standard enthalpy change for the reaction using thermodynamic data. So this is just using enthalpy of formation, the products minus the reactants, where O2 is 0. And then you have the formation enthalpy of ozone here. So you just add in the values. Remember to multiply by the stoichiometric coefficients, and then you should get the answer. Pretty simple question, which is why you only get 1 mark. And then state why the standard enthalpy change of formation for oxygen is not given. Well, it's because it's in its natural state, elemental state, I mean. So anything in its elemental state, for example O2 and H2 and most bimolecular gases, have a enthalpy of formation of 0. Okay. Calculate the standard enthalpy change for the reaction, entropy change this time, using thermodynamic data. So it's the same procedure, but this time just use the values for entropy instead of enthalpy. And then you have the same type of calculation. The next one, changing Gibbs. Whoops. Just use the Gibbs equation, put in the values, temperature that you have already converted in Kelvin here, and then you get the Gibbs free energy. Deduce whether the reaction is spontaneous or non-spontaneous. So when the Gibbs free energy is less than 0, it's spontaneous, and if it's more than 0, it's non-spontaneous. And in this case it's less than 0, so it's spontaneous. Okay, and then you have ozone depletion. You get 3 reactions explained by reference to bonding in O2 and O3. Which of the reaction needs more energy? So a shorter bond is a stronger bond, which needs more energy to break. And since ozone is conjugated, it has a like 1.5 bond, which is longer than a double bond. So the double bond requires more energy to break. So the first equation should be the one, yeah, which needs more energy. Oh, you need three arguments because it's three marks. So double bond, half bond, and then y, like which one needs more energy. Okay, using dichloromethane as an example, outline the reactions in which ozone depletion occurs in the upper atmosphere. So it's a 5-mark question. So you have to write 5 equations, and they're all radical reactions. And what you want is a free radical from the first reaction. So the way to write UV is usually like this. And then you should get something like this, where you have a free radical, chlorine radical, I think. Yep. And this then this radical then just reacts as ozone depletion usually does. And you also have to include that C2Cl bond breaks because the fluorine is more electronegative, which makes the bond stronger. So you would break the chlorine bond. The rest of the reactions you just have to look in the book and remember, I think. They're a bit tricky to remember, I also don't remember them perfectly. Okay. Next one, organic chemistry. Okay, you get some information, and artovastatin has the structure shown below. Identify the 4 functional groups. So let's start with 1. I don't know why this is in the IB syllabus because it's not in the book, but a nitrogen with a carbonyl besides it. It's similar to a amide, where you would have a O here, but this time it's a nitrogen, and the functional group is called amide, which I don't think it's in the IB curriculum, but anyways. Number 2, this one it's called a Benzene Ring, but I think they're asking for a phenyl. I think phenyl ring. Is that what they want? Yeah, phenyl. Yeah. And here you have a carboxylic acid, so carboxylic acid. And here is just alcohol or hydroxide, I guess. Hydroxyl. Carboxyl. Do not allow carboxylic acid, and do not allow alcohol or hydroxide. Well, that's weird. Apparently they want carboxyl and hydroxyl, so well, fine, I guess. Very picky. Yeah. Okay. Painkiller, blah blah. More information. Analysis on the sample. Carried on food safety. Following percentage compositions by mass. So it wants to find the empirical formula, and this is done by dividing. Oops, 66 but 99. Empirical formulas are found by dividing the percentage mass with the molar mass. And then you do the same for like carbon, hydrogen, nitrogen, and oxygen. And the remainder is of course just 100 minus the sum of these 3. And then you should get some mole ratio, and you divide by the smallest in the ratio, and then you should get an integer ratio, which in this case turns out to be approximately 9.5 to 10 to 1 to 1. And then you multiply by 2 to get the integers, and then you get this ratio. Yeah. Okay, so you don't always get the integer ratio, but you get like the smallest ratio, and then you multiply so that it turns into a integer ratio. Okay, the molar mass is this. Calculate the molecular formula. So find the molar mass of the empirical formula, and then see how many of the empirical formula you need to add up to the molecular formula. So in this case, it's apparently just 1. So if you add up the molar masses you find from this question, it should turn out to be 308.36. Okay, and then deduce the degree of IHD of buttes. So IHD equals 2 times the number of carbons plus 2 plus nitrogen minus hydrogen minus halogens, and then divided by 2. And in this case we have, from this one, 19, 22. So you have 38 plus 2 minus 20, I think, if I remember correctly. Yeah, 20 plus 2. That divided by 2, so this is 40. Oh, no, of course not. So 40 minus 20, 22, 11. I think should be answer. Yeah. Yeah, 11. Great. Next one, using information from section 26, which is IR data, I guess, because that's what the question is about. Identify the bonds corresponding to A and B. So I guess at least at this one it's carbonyl because it's approximately 1800 and it's sharp. So this is a C double bond O. And this one doesn't, like, it's at alcohol wave number, but it doesn't have like the broad peak. So it's at least not a alcohol with hydrogen bonding. So I think it might be a amide or a non-hydrogen bonding hydroxyl group. But in this case I would go for amide. No, amine of course. Yeah. Okay, OH and N2H actually. Frequency stretches due to which occur above, which are not present. Am I looking at the correct question now? Okay, here's the question. C2H. Apparently this is a C2H, which I didn't know by heart. So I guess just look in the data booklet then to find the one corresponding to a wave number approximately here, and like not the sharp peak and not the broad peak. Okay, here's the next one. One bond containing oxygen and one bond containing nitrogen that could not be present. Well, we now know that it's oxygen, like a hydroxyl and a amine, because it's not over 3000. And bond containing nitrogen, yeah, that's the amine. And then you explain. Okay, this paper is just never ending. Alcohol exomolecular formula used as a disinfectant has the following HNMR. 3 peaks, chemical shifts. From the integration trace, estimate the ratio. So here use a ruler to find the length from like here. Oops. From here to here. And then you get some kind of length, and a length here, and then you divide everything by the shortest length. And then you should get the ratio. Which in this case it's 1 to 1 to 6. So we can just write that. Okay. Deduce the full structural formula of X. Okay, so you have a molecular formula, and you know that is a alcohol. So it could either be this one, or it could be this one. 1, 2, 3, 4, 5, 6, 7. Okay, let's count 1, 2, 3, 4, 5, 6, 7, 8. Yeah, it adds up. And from here we see that this one is very much split, which indicates that it's this hydrogen probably because it's split between 6 different hydrogens here. And then you also have a 6 hydrogen trace here, which would be the hydrogens here. And the one which is really shifted is this hydrogen, and then you have the OH hydrogen here. So the full structural formula would just be 2-butanol, 2-propanonamyl, 2-propanol. Yeah. Okay, Y is an isomer of X containing a different functional group. State the condensed structural formula of Y. Okay, isomer means that the structural formula is the same. C3H. Oh, so what I'm thinking about right now is, let's see. Different functional group. Oh, no, there's no double bond presence there. Present. So it's probably a ester of some kind. So for example, like this. So 1, 2, 3, 4, 5, 6, 7, 8. 8 hydrogens, 3 carbons, and 1 oxygen. And it seems to be correct here. Okay, compare and contrast expected mass spectra of X and Y. Okay, so one similarity, they will both have a methyl. But the difference is that this one may have a ethyl as well. Yeah, this is the methyl, and then the different fragments, basically. Okay. It's soon done. That's great. Okay, both X and Y are soluble in water. Deduce whether or not both X and Y show hydrogen bonding with water molecules. Okay, so for something to have a hydrogen bonding, you need a O to H bond. So the only one with the O to H is the compound X, while Y has no O to H, it has only O to C. Yeah, and then you just show how hydrogen bonding works. Yeah. Okay, the two isomers of platinum, okay, it's some kind of complex ion, are crystalline. One of the isomers is widely used as a drug in treatment of cancer. Draw both isomers of the complex. Okay, I don't know, I'm not sure if this is in syllabus, but for a tetrahedral complex with 4 arms, there's a one which is called trans and one which is cis. So if you have them like this, where the constituents are 180 degrees apart, I think this is the trans. And then the cis one would be with them on the same side. Like that. So here we have chlorine diagonally, and here we have them on the same side. Okay, I drew the like the wedges and dashes wrong, but the one with cis is when they're on the same side, and the trans is when they're 180. Yeah, and names are not required, and like the wedges and dashes are not required. Next one, explain the polarity of each isomer using a diagram to support your answer. Okay, so for this one, both chlorines pull equally opposite directions. So this is non-polar, while for this one they pull in, like, they have a net pull towards this direction, which makes this one polar. And that's also how they do it, yeah. And state a suitable method other than looking at dipole moments to distinguish between the two isomers. Maybe NMR. I'm not sure. Look, let's see. Oh, okay, except NMR. But X-ray crystallography is the one which is, I guess, most widely accepted, because I don't think NMR for the distinguishing between complexes are covered in the curriculum. But X-ray crystallography is apparently. So that's it. Okay. 2 more questions. Compare and contrast the bonding times formed by nitrogen in the complex. So we have 2 types of nitrogen bonds. The one here between the nitrogen and the platinum, and one between the nitrogen and the hydrogen. So both are covalent bonds, but this one is a coordinate bond, because you have nitrogen lone pair here attacking the platinum, while here you're sharing the electrons. So that's the difference. One similarity and one difference. Deduce all the intermolecular forces between molecules of ammonia. So that would be London, dispersion, dipole, and hydrogen. I think. Yeah. All 3 of them. But you just need 2 of them, I think. No, okay, you actually need all 3 correct. So London dispersion forces, they're a part of all types of bonding because it's like the electrons are in random motion, so sometimes there's temporary dipole in a molecule, which gives rise to a London force. The dipoles are if there's a permanent dipole, which there is in ammonia, because you have a lone pair, which creates a dipole. And the hydrogen bonding comes from the fact that we have NH bonds, so this can bond with another ammonium. Like, let's see. Well, it's not actually an arrow, but like this bond coordinates to the lone pair here, which creates a kind of strong, a pretty strong OH bond. So that's it for this paper. It wasn't that fast going through anyways, but it was faster than how we would usually do a paper 2. So yeah, thanks for watching.